Just a quick disclaimer before we're getting started. Everything that I'm going to explain here is how I understand it. So this is what I truly believe to be correct. However, I'm only 21 years old and I'm still just in the process of learning. I love programming and I love computer systems and all of the binary and all that stuff. However, if I get things wrong, please don't be too hard on me. I'm just a 21-year-old kid. And I'm still working on learning. Please let me know in the comments so that way I can learn and everyone else can learn what I did wrong. Anyways, let's get started. So converting from hex to binary and back, we first got to know about each of the number systems. So we've got our default number system, which is base 10. That's what we're common with. That's what we know. 0 through 9. Each of these we can say are a symbol. And that way when we're talking about hex, we can see there's an F. And that is just the way a number is represented. So we can represent the number 10 as the letter A, and that will only take up one spot in our number. And so just a simple way of thinking of how the numbers count up is we add 1 to the number every time we're working. And once it hits the max value, it will then set the number that it's currently at to 0, and then it will cascade leftward. So if the next left number is that max value, that will then be set to 0, and then it will add 1 to the next one to the left. So in our base 10 number system, let's say we have the value 9. Well, this becomes 10 when we add 1 to it and when we're counting up. So that max value 9 then cascades up. Let's say we have the value 99. That becomes 100 because that first 9 becomes 10, and that 1 is then added to that second 9, and that pushes it up. So we can say in the case of binary, we've got 001. Well, this then becomes 010, or we could remove the zeros. 1, we add 1 to that, and that becomes 10. And again, with hex, let's say we have F. This will then become 10. And let's say we have FF, we add 1 to that, and that will become 100, okay? So that's kind of how the number systems work, counting up. Now, talking about conversions, let's first talk about the different sizes a binary number can take. So just a 1 or a 0 is called a bit. And now 4 in binary, that's a nibble. And then 8, that's a byte. And the reason why we separate it up into a bit, a nibble, and a byte is because we can easily convert between nibbles and hex. And the reason why it's so important to convert from hex to binary and not from hex to our default base 10 number system or binary to our default base 10 number system is it's really, really difficult, especially when you're working with larger numbers, to make these conversions to our default number system. And as you'll see, if you keep going along and you're viewing assembly and all of that, you'll see it makes a lot more sense in hexadecimal than it would in our default base 10 number system. And again, the ease of converting between hex and binary it's so easy to do that there's just no reason to use our base 10 number system. At least for the majority of cases. Now, of course, there's always going to be some cases where you'll need to use the base 10 number system. We're just talking about the majority of cases. So what we can do to convert is, let's say we have a binary number, 1010 and then 0011. We can split this up by nibbles. And even if the number is some odd number, right, where it doesn't necessarily match each nibble, we'll just split it up from the right going left, and so this will be another one, and we can add a 0 to the front to make that then its own even nibble. But let's stick with this byte of data right here, and in hex, a byte of data is 2 values. And so all we have to do to convert is we just take this first nibble and write it down as hex. And this one is the number 10, so that is A, and then this one is the number 3. So in hex, our value is A3, and that's what this value is right here in binary. So we, in the end, get A3, and that's just how simple it is to convert into binary. Now, let's try doing that with base 10 to just show that it doesn't work. So again, this is 10, and this is 3. If we use a calculator, so Windows R, Calc, we can see, and I've set this to programmer, that if we put hex, our value, A3 here, we get the same exact binary number, but the decimal number, or base 10 default number, is 163, and that is not 103. So converting between our default and hex and binary kind of doesn't work. So we're just going to stick with hex and binary, and this using hex and binary definitely makes, in my opinion, things a whole lot easier to understand what's going on behind the scenes. All right, now we're on how variables store data. This is going to be super fast. Basically, a character is a byte of data, an int is 4 bytes of data, and a long is 8 bytes of data. In Windows, that's not necessarily the case. When you're using C++ or any other language, there's generally a way to check the size. So in C++ and C, it's size of, and then whatever our value is. And if we do size of long and try and run that in Windows, we actually get the same size as an integer. And I believe, and I could be wrong, but I believe that's due to legacy code. So many people were using long as 4 bytes that they never updated it. And when they then were going to update it, it just would have broken too many things. And so they decided to make a long in Windows the size of 8 bytes, not just a long. Signed and unsigned values are pretty important. A signed value, all that is it's a negative number. Unsigned is a positive only number. Let's say we have a signed nibble. This first value right here, the number 8, this would be negative if this is 1. If it's signed, the leftmost value is the only part that's negative, and then the rest of these will be added to that negative value to get our total negative value. So unsigned values, this is just the number 8, and so unsigned values generally are bigger positively, but they both can hold the same amount of data. Signed is just negative. So let's say we wanted to show the value -4, that would just be this, as this is 8, -8 plus 4, we get -4. All right, now for bitwise operators, these are pretty similar to what we're used to, our Boolean operators, but they compare just across bits. So let's say we have a number 1111, and we are using the bitwise operator, and we can display it like this just to show more clearly what's going on, and it goes straight down. So the first value is 1 because they're both 1. The next value is 0 because only one of these is 0. Then 1 again, then 0. And that's what an AND is. It compares straight down. With an OR, this will all be 1s because both sides have 1s. And with an exclusive OR, one that you may not have heard of, only one side can be true. So this first one will be 0 because both are true, and it's exclusive. Only one side can be true. The next is a 1, then a 0, then a 1 again. And the last one, we only need one part of this. This will be our negate, and this just swaps how the values look. So in this case, it's actually the same as what we had for our XOR. It's 0, 1, 0, 1. Those flipped. If we add a 1 here, then this would become a 0. Bit shifting is pretty simple in and of itself. Let's say we have 4 values and we want to move it. We can just say that. We'll move it over 1, and this will become 0, 0, 1, 0. Basically, as the name kind of dictates, it is shifting all of our values and then appending a 0 to the end. Make sure that you know what you're doing in case of size, because if you bit shift, let's say we have a 1 here, then this 1 is lost. It's not appended to this because it can only hold 4 datas. Bit shifting the other way, 0, 1, 0, 0. We get, if we move it over 1, we get 0, 0, 1, 0. And so that's kind of how simple it is. We can change this number, and that's how many places it's moving. And we're doing this with unsigned values, as not all signed values will be the same, I believe. It can have undefined behavior because remember, you're working with a negative. For sake of simplicity, we're just going to stick with our unsigned values. Endianness, this actually will cover pointers a little bit here as well, but let's draw out a table. All right, and I did that with a little bit of fancy art, but we have all right. But we have each of these spots, and each of these this is our memory table, so let's actually title that. So this is our memory table. We're just showing kind of what it would look like in our RAM a little bit. These values here we won't know for the most part unless you're really going deep into the assembly and like you're building your own OS. You probably won't know what these are. Normally it's the like current free space that the program's on that it's just assigning values to. But for sake of simplicity, we're going to say that this is our 000 memory address, and so each of these bytes is kind of incremented. So this is 0000, 0001, 0002, 003, and so on, right? Endianness, let's say this is an integer. If we remember from before, an integer is 4 cells, so all of this is an integer. How we would store the number 9 is we would store it here, and basically it's like stacking it. So down here, we see 9 as 00000009, but it's stored in memory as 09, then these zeros. So the least significant is stored left, the most significant is right. I believe I'm saying that right. I could be wrong. But our value, this 9 right here, that very small number, is stored on the very far left, and it's kind of just flipped for how we'd see. So let's say we're trying to say hello world, or maybe just hello because it's a lot shorter. This would be an H, this would be an E, L, L, and then this would be O, and that's all little endianness is. Big endian is the opposite, so that's how we would expect, this should be an O. That's how we would expect to see it working out, is the zeros would be over here and the 9 would be over here. This would be HELLO. Little endianness is kind of backwards to how we would imagine it. Now, I'm going to revert this. Taking a little bit of selfishness, I love pointers. They're one of my favorite things of programming. All a pointer is it's just telling where this memory address is. So this is 5. So if we had a pointer, let's say we had char star A equals new char. Let's call this something like B, right? And this is in C++. So this right here, let's say we're currently at this address. The program is when it's running, so it assigns B to here. All the value of A is this cell right here, so it's 0005. It's not the B itself, it's just saying, hey, this is where it is in memory. Anyways, that's it.